Hello. So, welcome back to Night Science. We're in Bonding 2.0. This is somewhat what we did yesterday. That'd be Tuesday, October 14th. Um, so, I'm just going to fill you back in. We actually had presentations run over a little bit on Monday, the 12th. So, the 13th, we continue to do those presentations. So, you didn't miss a whole lot at the beginning there. Then we just continued on through the slides. And so you can kind of, that's where I'm going to pick up from there. Hopefully get us a little bit ahead of where we are at the end of class on 1013, and then get you started for the next level of that, this little mini lecture, if you will. So Bonding 2.0, this is Night Science Live, and yeah, let's keep. All right, so we picked up yesterday after the last presentations were finished with bonding foldable. You take a sheet of notebook paper and you fold it hot dog style over the holes, and we're going to label the very front of that ionic, covalent, metallic. All right, this is what it looks like. Oops, let's see if it's going to cover against my backdrop here. Okay, this is the foldable. Okay, I have a sheet of notebook paper. I have extra holes because I've hole punched so many times, but here's my main holes. This would be the top side right here. Top main holes of the page. Fold it hot dog style over. Well, actually I fold it the other way. I fold it towards the regular holes. I don't cover up the hole punch holes so that way I can still put it in my notebook easy. And I've got 3 sections to it, just like it's shown. Ionic, nope, that's metallic. Ionic, covalent, metallic. Does that make sense? That's where it is. That's what it looks like. And I have images drawn for what I'm about to show you on the slides. So we got a foldable. Let's see if I can make it bigger. Make me bigger. Against my shirt, it should show up. We got our ionic, covalent, metallic, and the pictures that go along with it. Notice it's just stick figures. So when I show the images on the next slide, just go back and look at my stick figures just to see my art is not very good. You just want to draw an image that represents each of those types of bonds. Those are the 3 chemical bonds we're going to look at right there. And so let's continue. We have here in the ionic bonds an image of an elderly woman, perhaps grandmother to this child. And that grandmother is throwing a ball. What I would have done is asked in class what does the ball represent in ionic bonds? Represents the giving of an electron from the grandmother to the boy. And in so doing, the grandmother's acting like a metal ion. A metal ion gives an electron and becomes positive, so that'd be a metal positive ion, a metal cation is what that's called. And the boy would be acting as receiving the one ball as a nonmetal anion, not anion, and cations are not cation, it's cation. You'll see that on the slide coming soon. The grandmother there acts like a group 1 metal, to be more specific, group 1A and 1, because she only gives one ball, which would be represented like 1 electron of the group 1 metals. That's what those do. The boy is only receiving 1 electron, so that boy is acting like a group 17 or group 7A nonmetal, like a fluorine, bromine, iodine, a halogen, otherwise known as. Now, if that boy were to receive 2 balls, one from one grandmother and one from another grandmother, the grandmothers would be acting like group 1 metals, and the boy would be acting like a group 16 or 6A. Because remember, group 16 or 6A with oxygen, sulfur, and others receive 2 electrons, and they can be from one source or from 2 different sources if those 2 sources are each giving 1, right? Because it can hold 2 extra ones. Anyway, this would be 2 minus, but in this case, we have a group 1 metal grandmother giving an electron to become to the group 17 or 7A non-metal boy. So that's going to make 1 positive, 1 negative, and opposites attract, just like the video you watched Mr. Edmonds singing it. This is true. This is the case. Covalent is an equal sharing of electrons, meaning they're just going to stay close enough not because of opposites attracting, but they're just going to remain close enough, get close enough so that the electrons that they would like to, the electrons that they can share, that are available to share, will actually go around both nuclei, kind of a figure eight style, if you will. Just imagine the odd shapes of the orbitals and understand that as those orbitals merge, it creates these hybridized orbitals, and the electrons can flow around both nuclei, which satisfies the whole rule. The whole rule is about the number 8, getting number 8. Bonds are a pathway for atoms to achieve the 8 rule of outermost electrons. So ionic species, they're going to totally give off or receive electrons, and that changes their outer electron number, makes it 8. That also changes their positivity or negativity, and then that attractiveness, that leads to an attractiveness between the two, positive, negative attract, and you've got a bond formed by the exchange, which satisfied the 8 number rule. Covalent, you've got a bond formed by these two atoms who have a mutual understanding of achieving the 8 number. So they're just going to share a couple of their electrons so that they can pretend they have this 8ness. So their proximity and their closeness to 8 already allows them to share just a couple electrons. They achieve the 8 status, and they're satisfied. Okay, metallic here, and that's why we show these two people doing a tug of war where the rope is like the shared electrons. Metallic are atoms whose elements have these extra electrons in d orbitals normally. These are normally transition metals that applies to the most. They'll form bonds with themselves. It's like a copper atom with the other copper atoms. They normally do that typically because they form solids almost always. They crystallize in these crystal structures. They're very tightly bound. And while they're so close together, the nuclei of the atoms will actually be so closely bound in their crystal structure that the electrons can flow freely from any nuclei around the way. They flow freely like ocean water. So we think of these electrons as like the seawater, and they can, when they're put together with other ones, they can flow freely. Just like if you pipe in water over a sea, it'll flow. If you pipe in electrons, it'll flow. Flow of electrons is called electricity. So metallic ions are just that way. So we'd say ionic is between a metal and a nonmetal. Covalent is from nonmetal and nonmetal. And metallic is metal. Now, if we look at our periodic table, we can actually see kind of a cheat way to understand this. A shortcut that works most of the time is to say that ionic forms between metals. That's all elements this side of the darkened staircase. Sorry, there we go. Nope. The darkened staircase right there. Everything on this side are metals, and everything on the other side are nonmetals. So that'd be left-siders are metals, and right-siders are nonmetals. Even the metalloids that touch the staircase, they can be considered as to acting like whatever side they're on. So even like aluminum is on the left side. Yep, is on the left side. So it's going to act like a metal in terms of these electrons bonding. Anyway, if you have something from the left side bonding with the right side, that's called an ionic bond. The only one exception is hydrogen, because hydrogen is not a metal. So the rule is only true when it truly applies to metals and nonmetals. Hydrogen is not a metal, so it counts as a nonmetal. It counts as being on the left, as a right side. Anyway, so I would say a compound between something like right here and right here is an ionic bond. If I said things bonded between themselves over here, that'd be metallic. And then things bonded between themselves on the other side and hydrogen, those would be covalent bonds. So we'll see some in a second to practice. Okay. All right, let's keep going. So on the back side, that foldable, flip that foldable directly over. We got chemical bonds. And you record the definition there on the screen. Pause now so you can have plenty of time to do that. Ultimately, I'm not going to end up giving you a lot of time to fill this thing out. But pause now, record that definition. Because next, we open up that foldable. And on the inside, we've got 3 panels: ionic, covalent, metallic, and we have definition, examples, and properties for each one of those different tabs, just as you've opened it up. Pause now, make sure you have those parts, but if you don't, that's okay, because when we start filling it in, like for ionic, it repeats those definition sections of definition, or those sections of like definition, examples, etc. I'll walk you through how ionic bonds works. Ionic bonds, a bond formed by the electrostatic attraction of oppositely charged ions. So we say that it's a bond formed by the positive and negative attracting. The positive and negative ions are attracting. How they became positive negative was to satisfy the 8 rule. So they attracted and they went together. Examples here are NaCl, K2O, Na2, CO3, or sodium chloride, potassium oxide, sodium chloride, potassium oxide, and sodium carbonate. And that's what it forms. Now, quick reminder on ions. Read this, pause and read it if you need to. Ions are charged particles, charged atoms who have lost or gained their electrons. Metals lose them, valence electrons, so they're called cations and become positive. There's a little mnemonic device, cats. They're positive, y'all. Anyway, corny as it may be, it helps you remember. And then anions. So no cations, no anions. It's cations are positive, anions are negative, and their nonmetals are anions or nonmetals. Take a look at that slide. Pause if you need to. Properties of ionic bonds: they form hard, brittle crystals, meaning they're solid, have high melting and boiling points, and they conduct electricity in liquid or aqueous form. Aqueous just means dissolved in a solution like water, so they can form crystals that dissolve. Think about sodium chloride as table salt, pour it into water. It can dissolve. That's what we kind of understand. It can conduct electricity only in those states. Also, when you see something like this, just as a critical thinker, I want you to think about when it says high melting point, what does that mean? It means that, it's a high temperature, like above oven temperature degrees, like above 300 degrees or more, at least above that. That means it's a melting point that's that high. And we don't live in an oven temperature. We live in well below that, like 200 plus degrees below that. So we live in normal conditions are usually well below oven temperatures. So if it has a high melting point, that means it has not melted yet during most normal conditions. If it has not melted, then that means it's a solid. So that's kind of a giveaway there. It's implicit to it, but it kind of requires a little bit of indirect thinking. Replay that section if you need to get what I'm trying to say. Now, I went through in class and I slid through these slides very quickly because I actually assigned the conclusion of that foldable, finishing it for homework. So you do the same, finish that foldable for homework, have it ready. It's due on Thursday, which is tomorrow. I know this video is being posted late for you, but these slides, like on the video I'm showing you, are on the bonding folder of the class docs folder in Google Classroom. I can show you that in a second. First, we went and labeled what kind of bond this was before we did that. Ionic, covalent, or metallic. This one is covalent because it has all nonmetals. Now, hydrogen, you might say, is from the left side of the periodic table. It is. Hydrogen is from the left side. Remember, it's a rule breaker. Hydrogen, as a rule breaker, still acts like a nonmetal, or is a nonmetal. It just has some of the properties of group 1. That's why it's there in the first place. It's still a nonmetal. That's the only rule breaker. Every other left-sider is a metal. All the other right-siders are nonmetals of the staircase, right and left side of the staircase. So this next one, AlCl, 3. Which one is it? Ionic, covalent, metallic. It's ionic because Al is a left-sider, even though just barely. Cl is a right-sider. The rule worked. Well, Cu. It's all left-sider. It's only left sides between itself. It doesn't look like it's bonding with anything, but it's actually a crystal structure of several copper atoms. So it is metallic. This is normally how metallic bonds are shown. It's just an element, which presumes multiple atoms. With platinum, same thing. MgCl2, Mg, left-sider, Cl, right-sider. That makes it ionic. If it's all lefty or all right-siders, carbon and hydrogen are all considered right-sided or non-metals, so it is covalent. You know, chronicle those. Another video there. We don't actually watch that video. Next up comes an exploratory activity that I'm going to post with this video to Google Classroom. That's kind of where we're going to decide. You can look at those as well. It's all document text. It's discerning rules and patterns from naming chemical bonds. I want you to go look at that right now. Take some notes on it. Upload it back. Send me questions if you need to. Send me your responses to those exploratory task items and then let me know. This may put you a day behind, but this is what we're actually going to finish up today on Wednesday, 10/14, October 14th. We started like last 5 minutes of class 10:13, barely started. So don't fret, you're not behind. Work on that today, finish that today, and then we'll move back through the slides. And if I were you, I'd jump back to the slides and get ahead of me so that way the next video I post, you can be ready to go. I might try to go live today during third or fourth period, not second. So if you're watching this today, just know that's coming for that period. Thanks for watching. We'll keep you in tune. Send me your messages. Do the actual lab that I'm showing that I'm going to be uploading with this video. Go Dogs.